So today what we are going to do is tests for goodness of fit. So what do I mean by that? You are assuming, so that your hypothesis, null hypothesis, is that your population follows a specified probability distribution. In many cases, what we will be interested in is some categorical data. So you have some categories, and for each category, you have a certain probability associated with it. And that's what you're assuming for the population. And you want to test if these probabilities which you have assigned to different categories, do they borne out when you take a sample? So test this. Test the probability distribution for population using sample data. In other words, you want to see that how good your sample is following the probability distribution curve. And if it's close enough to it, then you accept it. If it's veering far away from it, then you will have evidence to reject it. So for example, suppose you have a certain normal distribution which you believe holds for your population, and you know what its mean is, what its variance is, standard deviation is, and now you take sample, and from sample you plot the frequencies. So you can, for example, divide this. This is your variable. You can divide it into discrete bins. And for each bin, according to this distribution, there's a probability. Now you take samples, and in sample, you compute the frequencies. So for example, using those frequencies, you get a number here for the probability. For this bin, you get here, this bin, you get here. And this normal is kind of approximating the plots, the dots you got in your sample. So if it's close enough, then you are saying that your probability distribution curve is fitting your sample data. So in this sense, this is a test for, we are going to do tests for goodness of fit, that how closely our assumed probability distribution approximates what we got in the data. So in other words, we are assuming something, and using the data, we see how close we to the assumed probability distribution, and do some statistical tests. If those statistical tests fail, then we reject the hypothesis, and that means that our probability distribution is probably not what we started with, what we assumed. And these tests which we will be doing will all be chi-square test. For goodness of fit. So whenever you have a curve and you have some data points, one way to fit those data points is do the chi-square fitting. And based on how good your chi-square fitting is, you are going to decide if you are passing the test or failing the test. So let's start with what kind of tests will be involved. So for example, suppose this would be like, for example, suppose you have k categories in the data or in the population. So it could be any variable which you have divided into its range into nk bins, or it could be some attribute of the population which has k categories. And based on that, you make some observations. So for example, you have these categories 1, 2, 3, 4, up to k. And you have assumed probability for each category to occur. So for example, like if you have a population in a country and there are people from, let's say, 10 ethnic backgrounds. So now each category would be the ethnic background or a possible ethnic background of the population. And the probability would be just for, if you randomly select, the probability is simply the number of people from that ethnic background divided by the whole population. So that would be assumed probability. That would be the actual probability of the population, but if you don't know that, you are assuming that probability. So that kind of thing is defining your categories. Or for example, you could be talking about preference for certain brands. And this could be k brands of a product, of a certain product. And then the frequency of people who prefer each one of them, if this is one of these brands is their best preference, then that frequency would be the probability of this category occurring as their first preference. So for each category, you have a probability, assumed probability. Let's call them P1, P2, P3, P4, up to Pk. Now, based on these assumed probabilities, if you make a sample of size n. Now, make a sample of size n. Then you have picked n elements from the population, and these are the probability given. So now you can compute your expected number of each category occurring in sample. So since you have n total number and the probability of each one of occurring is P1, P2, and P3, and so on. So this probability, this expected number would just be n times P1, where n is your total sample size. This would be obviously NP2, NP3, NP4, and so on. But obviously, this is just probabilistic. You have made a finite sample. You don't expect exactly this to occur. So your observed numbers will be different. So let's say they are O1, O2, O3, O4, and so on. Then, based on this data, you can compute a chi-square variable. So first of all, when will this test work? You need each one of them expected numbers. If expected numbers are greater than 5, then the chi-square test can be applied. And what's the test? You compute this chi-square variable. The chi-squared variable what's the variable? You have, if you have k categories, it will be have k minus 1 degrees of freedom. So essentially you are fitting a square deviation, your observed value, and what you expected, divided by the expected, and you sum over all the categories you have. And the combined chi-square differences, combined square differences which you have, they are collected in this chi-square variable. If you were exactly following your expected probability distribution, then obviously your observed and expected difference would be negligible. It would be 0 and your chi-square would be 0. So the closer to 0 you are, the more confidence you have that your observed data is following your assumed probability distribution. But if this doesn't happen, if they are like slightly above or below, doesn't matter if they're above or below, you're computing their difference and squaring it over here. And you collect all those differences, all those squares of differences to compute an overall chi-square variable. And if it's too large, then that means that your assumed probabilities are probably not the correct ones for the population. So based on that, you can say that I can do the test and I can reject my starting hypothesis. That what is your hypothesis over here? This is your null hypothesis. So these are your probabilities in the population for these categories. So then if your chi-square, if these differences turn out to be too large, then you can reject H0. So when do you do it? If this thing which you have computed is greater than a critical value, like if it's too big. How big? Again, it depends on your significance level. And as always, you are defining this critical value to be that value of the chi-square for which chi-square occurring taking a value larger than this number is just alpha. So chi-square variable is something like this, and you are just looking at this tail with area alpha, and this critical value is chi k alpha. So pretty easy to do it. And let's take an example. So for example, let's suppose you want to, there are 3 news channels, 3 local news channels, and you want to test Are they equally popular or not? So equally popular would mean that if you ask the viewers which one is your first preference, they will pick. So let's say these channels are A, B, and C. If you pick a person at random, so 1/3 of the population prefers A, 1/3 prefers B, and 1/3 prefers C. So if you pick a random person, the probability of them answering that their first preference is A is 1/3 is 0.33. Same for B and same for C. And suppose a survey of 150 viewers was done, and these are the numbers, their first preferences are recorded below. So these are your categories: channel A, channel B, channel C. And you observed first preference for channel A, it turned out to be 47. Observed preference for channel B turned out to be 42. And 61 people in the sample said that they prefer C. They're close enough to 50. So just looking at them, you can't say if they are equally popular or not, because you have taken a finite sample. So to make a quantitative statement, you have to do a statistical test. And this is your null hypothesis, that the probabilities were 0.33 or 1/3, 1/3, 1/3. They were equally probable. And based on these probabilities, your expectation was that if you do a survey on 150, A should be around 50, B around 50, C around 50. Now, given this data, you can compute the chi-square. And since you have 3 categories, you are doing it for the 2 degrees of freedom. 50 square over 50 plus 42 minus 50. This is this number. Plus 61 minus 50 square over 50.
Sir, can you hear me?
Say again?
Sir, can you hear me?
Yeah, I can.
I wanted to ask, where did you get the probabilities of 0.33?
Oh, because this was my, this is the null hypothesis I wanted to test. So see, what's the question? You want to test, are they equally popular or not? So I start with my null hypothesis that they are equally popular. So equally popular means that the probabilities are 1/3, 1/3, 1/3. Because the total probability
All right, sir.
is going to be 1. So all I have to do is compute this number. So 9/50 plus 64/50 plus 121/50. So that gives me a number. If I put these things in calculator, I'm getting 3.88. Now, I want to test, let's say, test at significance 0.05. So what's the probability at 0.0005, the chi-square value if I look for this critical value, this turns out to be, let me just compute it from the stat track. So if what I have to do, I have degrees of freedom 2 and probability of chi-square being greater than this critical value, I want it to be 0.05. So this gives me the critical value 5.99. So since this thing, the observed chi-square 2 is less than this critical value, I cannot reject H naught at 0.05 level. So I can't say with 95% confidence that they are not equally likely. I have to stick with that probably they are equally popular. These differences are within my expectations of random fluctuations. Actually, I can try to compute the p-value of this test with this sample. So that means I have got this number and I have to see what is the probability. P-value would be simply probability that chi-square of 2 is greater than my observed value. So if I do that, for 3.88, the probability of chi-square being greater than 3.88 is 14.14. So the p-value is 0.14. I have some evidence that probably they are not equal, but it's weak because the p-value is not very small. I can take a little bit more complex example. So suppose I look at this one. Wait. So suppose there is some product and they have different flavors. Flavors A, flavor A, flavor B, and flavor C and D. So there's a company which sells these 4 different flavors of a product. Let's say it's a yogurt. And from the sales record, they know the preferences of people, that 20% of the customers they prefer flavor A, 35% ordered flavored B, 0.18% ordered flavored C, and 0.12 ordered flavor D. You should note that, as I should expect, that if I add them, their sum should be equal to 1. Now, what they do, they run an ad campaign, and they think that these flavors are not doing that good. So they run an aggressive advertisement campaign. And after the advertisement, after 1 month of advertisement, they go out and they take a sample. They ask people which one you like now. So they take a sample of 80 people, random sample, and see, has the ad campaign affected these preferences? So that would mean, have these probabilities changed or not? And the observed values turn out to be, well, first of all, we can compute that the null hypothesis, this is still their null hypothesis. That's how they start, that the probabilities which translate to preferences in this case have not changed as a result of the ad campaign. So this is the null hypothesis, that these 4 categories have these probabilities associated with them. So they take a sample of 80 customers. What is the expectation in sample? So it's simply, this is 80 times 0.2, which is 16. This is 80 times 0.35, which is 28, and this is 80 times 0.18, which is 14.4. You should note that although our actual sample will only have whole numbers, because these are like complete people, but it's better to just leave it in the expectation value as a decimal. Now this one is 9.6. So they should be seeing, they want to see, because you want to leave it like this, because if you get a number 14, still this small difference does matter in your statistical analysis. So you leave it like whatever exact number you get. Now, when they did the sampling, the observed values were, if I read from here, this was 12, this was 16, this was 30, and this was 7. So first of all, you should notice that since the expectation values are greater than 5, so I can do the chi-square testing. And to do the chi-square test, I have to compute chi-square. This time it's a variable with 3 degrees of freedom because I have 4 categories. And I just make this difference. Divided by the expectation for this first category. Plus 28 minus 16 divided by the expectation plus 14.4 minus 30 divided by the expectation plus 9.6 minus 77 divided by 9.6. So all I have to do is compute this variable, and I'm gonna try to do it. Let me just directly do it on the calculator, trying to put these numbers in.
Sir, पहले हो रही थी record. अब शायद हाथ. Yes.
Okay. So I make these 3 bins and I compute. So I can call these categories students, category A, students with less than 60, less than or equal with marks less than or equal to 60. Category B, students with marks less than equal to 80 but greater than equal to 60. And category C is students with marks greater than 80. So I have these 3 categories, A, B, C. What are the probabilities for a student to be falling in any of these? So I know that for one standard deviation, I can just compute for the standard normal. The probabilities for 1, 2, or any number of standard deviation is same if you compute it for your specified normal or for the standard normal. So the probability of your normal variable being less than -1, that will correspond to this one. Is simply 0.159 or 0.16 that we know. And probability similarly of z being greater than 1 is 0.159, is symmetric. This is -1, this is +1. They are both about 0.16, which I am taking to the third decimal 0.159. So then the probability, the rest of the probability of z being -1 and +1, that's 0.682. So it's 0.159, 0.682, 0.159. Now, I expect based on this, so suppose I make a sample. Now I take a sample of 200 students. Then my expected number, which out of these 200 students, which falls under this, is simply 0.159 into 200 in this one, and 0.682 into 200, and 0.159 into 200. So this is 31.8, this is 136.4, and this is 31.8. That's what I expect. You can see that since the normal distribution is symmetric, and so one deviation on one side and the other, I'm expecting same number. Now suppose that when this 200 students were sampled, these were actual observed number of students which had less than 60, 25 here, 130 here, and 45 here. Now the question is, based on this sample, can we say that they are following normal distribution? Now, this statement will obviously not be a truth or false statement about the actual probability distribution. We cannot categorically say, we won't be 100% sure if the actual distribution is normal or not. It's only based on this limited data, what we can do. So since we always have limited data, limited evidence, that's why we do this kind of testing, that we start with a hypothesis and we only go towards rejecting it if we have enough data. So my H0, which was that probability distribution is normal with these specified parameters for its mean and standard deviation. I can say something about it. This translated into, by taking this data into these three categories, this translated into 3 category probabilities, which are written here. And essentially we are testing these probabilities using our previous method. So the method worked by picking a certain number of categories, and if we had an assumption about the probabilities of each category, then we can test it by observation. So that's what we are doing. Now, so what I need to do, I need to compute this chi-square, and since there are 3 categories, so this has 2 degrees of freedom. So looking at these columns, 31.8 minus 25 square over 31.8 plus 130 minus and when I compute this, I get 1.45. So this gives me, let's see, what does it give me? 5.51. 7.26. So this number is pretty close. This is also not very far away. This is slightly, one indication is that these two numbers are not equal, which we expect to happen in a normal distribution. So now I can check that, let's say, or maybe I can just directly compute p-value. And this turns out to be, I have 2 degrees and my critical value is 7.26. So this gives me 0.03. So that means this number is quite large. So I can reject. It's not with the significance 0.03. So there's a strong evidence that this starting assumption about this particular normal distribution is probably not true. We can do similar examples for other probability distributions as well. So for example, let's consider this one. So let me just do this one. So for example, there is test for, okay, let me first write what we are doing. So we have a highway toll booth, and in a period of 100 minutes, we observed it for 100 minutes. In 100 minutes, 190 cars arrived there. So we want to test for Poisson distribution. That did they follow Poisson distribution or not? So we have these categories: number of cars in 1 minute. So for example, there could be some times when no cars arrived. So this is observed numbers. So there were 10 minutes where no cars arrived. Then there were 26 such minutes where one car arrived. And 35 where 2 cars arrived. And 24 where 3 cars arrived. And there were 5 such minutes where 4 or more cars arrived. So we want to see if this follows the Poisson distribution or not. So to check that, for each category, I should see what does Poisson tell me. So Poisson distribution is given by this. Where n is this number. And lambda is the mean. So the mean we can compute very easily over here. Mean number of cars per minute is 1.9. And those probability for 0 cars per minute is e minus 1.9, 1.9 to the power 0, 0 factorial. So this and this become 1. All I have to compute is exponential raised to the power minus 1.9. So 1.9 this gives me minus, this gives me 0.14, well, almost 0.15. So the frequency over here, the probability, let me just write it here. Abilities. This one was 0.15. And if I want to write expected numbers, then I have 190 times this 0.15. Okay, I'll write these below. There's no space here. Let me first just compute the probabilities for these. So for each one of them, I can compute these numbers. This is fixed for all of them. And this is 0.15. So I keep it like that. So the second probability for 1 car per minute is simply 0.28. And probability for 2 cars is over 2 factorial. So it's 0.27. Probability for 3. Three factorial. So it's 0.17. And I can find probability for 4 or more by simply summing them. They sum So it would be simply 1 minus 1.7. So this gives me 0.15, 5, 0.125. So I've got all these probabilities. I can put them in this table over here. And then by multiplying with the number of cars, I can get this here. Maybe I should make a new table. Or should I erase this? Let me erase this for now. Let me see if I can move it. Okay. So I have 0.15, 0.285, 0.27. Point 0.17 and 0.125. These were the observed, and expected would be those probabilities multiplied with the total number of cars. So $28.5, 0.285, 54.15, 0.27, 51.3, 0.17, 32.3, 23.
Sir, what probability are you getting for 4 or more
Yeah.
cars in 1 minute?
What about it?
What probability are you getting?
0.125.
0.125. So I got 0.08.
Really? By doing this?
Oh, what I did is that I used the same formula, but I put 1.9 to the power of 4 and then 4.
Yeah, because I'm saying 4 or more, because I want the total probability to
Okay,
be
I
1.
understand. Okay. All right.
Okay, so all I have to do now, the same thing. I think I should not do the calculation. Make these differences, difference square plus difference square, add all of them, and then make this chi-square, which is a variable of 3 now, because I have 5 categories, so it's a 4. And I'm computing numbers like this: 10 minus 28.5 square, and put the expected here. All of these, and then all you have to do is check if this is greater than So suppose if you're testing at 0.05 significance level, if true, sorry, reject H naught, which is that the Poisson distribution is the probability by doing this. And to do that, you will have to compute this. Well, there's a slight technical detail. Do not use chi-square for 0.05, but chi-square for 3. So this gets replaced with a 3. The reason is that if you are, we are just testing that if it's Poisson or not, and we don't know if it is Poisson, then what is the true mean of the Poisson? We got the mean by doing a sample. We observed for 100 minutes and picked a sample of 190 cars. So based on these 190 cars, we got a mean. So that mean is an estimated mean. So if you have if you are making an estimation, then you have to, for each estimation for the parameters of the population you make, you have to reduce the degrees by 1 because you have less information to constrain your curve fitting. So that's why instead of 4, you get 3. And then all you have to do is check this. In this case, I think I won't have time to compute it, but you can now go and fill the calculation and you can reject or accept it. So let me stop here. What I'll do, I'll upload another lecture which was missed last time shortly after this class.
Sir, I have a question about the final exam.
जी.
Sir, वो final exam online होगा या फिर?
Online तो allow, they are not allowing it.
अच्छा. और syllabus वही जो शुरू से है या फिर आप shorten करेंगे syllabus?
नहीं, सब कुछ what we have done so far.
Okay, sir.